Hello dear students, let us begin with our today's video lecture 2 of the chapter Magnetism and Matter. Today's topic to be discussed are magnetic field lines and its properties, bar magnet as an equivalent solenoid. Let us begin with magnetic field lines and its properties. Magnetic field lines. These are visualization of the magnetic field around a bar magnet. As we can see here, if I assume a bar magnet having north and south pole, we already know that from our lower classes that north pole the magnetic field lines will start and they will end at south pole, which you can visualize in this manner. The arrow marks point out the direction of magnetic field around the magnet. Moving ahead, let us try to have a look at the properties of magnetic field lines. Magnetic field lines of a magnet form continuous closed loop. That means they do not end from or start at any place. They are continuous. So as you can see in the screen, they even pass through the magnet. To specify it more clearly, the magnetic field lines move from north pole to south pole outside the magnet, and they move from south pole to the north pole inside the magnet. Second property, the tangent to the field line at a point presents the direction of net magnetic field B at that point. So if I assume any point on the magnetic field lines and I draw a tangent at that point, then that tangent will give me the direction of magnetic field at that place. If I assume 4 points here and if I try to take tangent to those points respectively, then those tangents will give me the direction of magnetic field at that place. The magnetic field lines are almost similar to the electric field line concept, except in the case of first property, because magnetic field lines do not end or start from a particular point. They are continuous. Taking the next point, larger the number of field lines crossing per unit area, stronger is the magnitude of magnetic field in that region. So if I assume two circles covering equal areas, we can observe that in this area there are more number of field lines passing through it compared to this one. So I can clearly say that magnetic field strength is more here compared to this region. Taking the next property, magnetic field lines do not intersect each other. It is similar to that of electric field, and the reason is if they intersect, then magnetic field line or magnetic field at that place will not have unique direction. So if they intersect at this point as shown here, this place, then magnetic field will have two direction, which is not possible. Next, so now let us start with bar magnet as an equivalent solenoid. Here we try to take magnetic field lines of a solenoid and magnetic field lines of bar magnet. If we compare them, then we find that both are almost similar. By looking at this diagram, you can see the magnetic field line around a bar magnet, and beside that you have a solenoid which is almost similar to that of bar magnet. We need to prove that the magnetic field due to both of them will have same or will be almost similar. So a bar magnet can be thought of large number of circulating currents around the bar magnet. So let us try to prove this. Let us try to consider a solenoid of n turns per unit length. So assume that this is a solenoid. Here there are plenty of windings over it which can be visualized by you. Let us try to take axis on this one such that the center of the axis is the center of the solenoid. Let 2L be the length of the solenoid and A be the radius of the solenoid. If the 2L is the length of the solenoid, then half length will be L. Moving ahead, let us assume a point P on the axial line at a distance r from the center of solenoid. So if I assume point P here, then from the center the point P is at a distance r. Next, let us consider a small segment of the solenoid, just like a thin ring of the solenoid. I am going to take a small portion of the solenoid, and you can try to take it like a current loop here. So the current loop's thickness is dx, and the current loop is at a distance of x from the center of the solenoid. So the number of turns in that circular element dx, so how many wires are there, how many windings are there in that, that will be equal to n dx. Further, by assuming this circular element to be a current loop, I can write the magnetic field using this formula here. So this one we have derived in the chapter moving charges and magnetism by using Biot-Savart's law. So this formula will help us to solve the present scenario. So here this is valid for a circular current loop, and in the present scene we are having a small thin circular current loop here. So we can find out magnetic field due to this using this formula, but there are some alterations we need to figure it out. That is, the x value what we had chosen in that derivation is a bit different in our present scenario. So according to the diagram we shall do some alterations to this formula. So in that discussion of circular current loop in moving charges magnetism chapter, we had assumed the radius of the circular loop to be capital R. Presently it is small a in our case here. So we are going to replace capital R with small a, and x is the distance from the center to the point P, center of the circular loop to point P. So presently the distance comes out to be R minus the x distance, so that I can be here. So x will take the positive values on the right hand side and will take negative values on the left hand side. Moving ahead, let us substitute these respective values in the formula to get the solution. So we get it to be dB is equal to mu naught divided by 4 pi into 2 pi n dx I a square divided by r minus x square plus a square whole to the power 3 by 2. So to find the total magnetic field we have to do integration. Now integration of these dx elements from this end to that end. From this end means from the length L to that end means length minus L, because on this side the length comes out to be negative, so this end of the solenoid becomes minus L and this end becomes plus L. Substituting their respective limits, we get the equation to be B is equal to integration from minus L to plus L, mu naught divided by 4 pi into 2 pi n dx ia square divided by r minus x square plus a square whole to the power 3 by 2. Moving ahead, we shall take the assumption of r much greater than a and also r much greater than x. This assumption makes x to be very small, assuming that r is too much greater compared to x, and also a is very small compared to r, that is distance of the point P is too large compared to a and x. So if it is this, then we can neglect a and x from this equation which comes in the denominator. So r minus x whole square plus a square whole to the power 3 by 2 will come out to be r square whole to the power 3 by 2. 2 and 2 will cancel out, so we'll get r to the power 3. Substituting this in the equation which we had got previously, we'll get b is equal to integration minus L to plus L mu naught divided by 4 pi into 2 pi n dx I a square divided by r cube. Moving to the next step, we are going to put the integration over dx, and the rest of the terms will be taken out of the integration as they are not going to get integrated with respect to dx. So writing all the remaining terms and integrating dx from minus L to plus L, we get this expression. If we integrate dx from minus L to plus L, we get the term x with the upper limit plus L and with the lower limit minus L, as you can see here in the screen. Moving to the next step, here we have to substitute the limits. Here the upper limit is plus L minus of the lower limit which is minus L. Further, the next step comes out to be mu naught divided by 4 pi 2 pi n I a square divided by r cube into 2L. So B comes out to be, the total magnetic field comes out to be mu naught divided by 4 pi into 2 into pi a square into n 2L into I divided by r cube. Assuming this to be equation 1, and let us have a look at the next part, what we are going to do. So here, considering this diagram, we shall try to speak about magnetic moment of the solenoid, that is magnetic dipole moment of the solenoid. So if I try to take magnetic dipole moment of the solenoid, we can write it like m is equal to total number of turns. How many turns are there in the solenoid? That one into the current flowing the solenoid into cross-sectional area. That is, we have studied this in moving charges and magnetism chapter. That is, total number of turn is n, current is I, and cross-sectional area is capital A. So that itself is magnetic dipole moment. Using that formula, we are trying to move ahead. Substituting those values of total number of turns in the present diagram. So total number of turns in the present diagram are not n, because n is number of turns per unit length. So total number of turns will have to be n into 2L, and current as it is I, and cross sectional area will be pi r square, that is area of the cross sectional circle. Okay, so this comes out to be equation number 2. Further substituting 2 in 1, then here you can see this equation 1. If I substitute 2 in 1, then pi a square into n into 2L into I will directly get replaced with a small m. That small m is magnetic moment of the solenoid. So if we write it, we get B is equal to mu naught divided by 4 pi into 2m divided by r cube. This is similar to that of the magnetic field due to a bar magnet on the axial line, so which we have studied in the previous chapter. So you can see that we have proved that bar magnet is equivalent to a solenoid, and the field of solenoid is similar to that of bar magnet. Thank you students, and we'll meet in the next video lecture.